Our next lecture is Multi-Messenger Astronomy by Professor Lili.
Thank you. Thank you for the organizer. And for me, it's very nice to have a chance to come to Baikal. Like, multi-messenger astronomy opportunities and challenges is quite a big topic, and it's covering pretty much everything, right? And actually, it's quite a new field. Multi-messenger astronomy, the first time appeared in the papers just in 1999. So only in 20-something years. Back to that time, people talk about multi-messenger astronomy mainly focusing on gravitational wave, gamma rays, and the neutrinos. And then later in 2003, okay, they add a cosmic ray in the field. After that, we have multi-messenger astronomy with such relatively young field, and then within these 2 decades, you already have a lot of observations and big success. And I think nowadays people already know what is multi-messenger astronomy. They include 4 messengers like gravitational wave, cosmic rays, gamma rays, and the neutrinos. And I don't want to show the picture with those 4 messengers, but I want to show something what we have with SED, energy spectrum distribution. For example, something like that. So for the photons, they cover quite a long range, like from radio to gamma rays. Nowadays, LASSO has already observed the photons with PeV energy range. It's such a big achievement. And then for the neutrinos, okay, some of the neutrinos from Big Bang, right, like a CNU B. And then we have the PeV neutrinos observed recently by ChemistryNet. And for cosmic rays, it's also quite a big energy range, right? From GeV until the GZK cosmic rays, they cross the universe. And even though we don't know their origin still today, but there are quite a lot of physics going on. And for the gravitational wave, like LIGO and Virgo, they observed the first gravitational wave, and then they get Nobel Prize. And also there are some other experiments trying to get the gravitational waves from different phenomenologies, like PTA and the spaceborne gravitational wave satellites. So that's a basic picture. So there are a lot of chances for us, especially for you young people, right? And there are a lot of options. You can choose one. You can choose one field and work on that. There are a lot of surely challenges. Why there is a gap here? There is no data from that side. What can they tell us? And also for the neutrino, we measured the neutrino from MEV to PeV, but for the lower energy, how do we do that? And how do we explain the origin of those neutrinos? And surely for the cosmic rays, there are a lot of models done, and how do they generate it? How do they propagate, right? And if we detect them, how do we know their mass composition? Like if they are proton, carbon, oxygen, or ion, right? Also for the gravitational waves, there are a lot of things to do. So let's talk about the brief history of the multi-messenger astronomy. It's starting from the radio, from our eyes actually. I have the Galileo for the first one because it's something like a modern astronomy. We use tools or we use instruments to observe our universe. Right before that, surely we use our eyes to see what we have, and there is a long history for a few thousand years. And then later, in 1830s, we have the first infrared. This field is quite by chance. So Herschel used a probe to observe the solar light, and for different colors, he measured temperature of that. And then he found out the range of the red light, there is something with even more higher temperature. So, okay, after that, he thought maybe there's something wrong. There might be we cannot see, not visible to our eyes, but they are there. So the name you can see, infrared, right? Infrared to after red. And then later we have the we have the cosmic measured by Victor Hess with a balloon. He took the balloon Geiger tensor and Geiger counter to get a cosmic ray. From there, we know, okay, the cosmic rays are not from our Earth, it's from outside of our Earth, right? With increased altitude, the cosmic ray counts get increased. And then later, 1930, also by chance, we have the radio astronomy. So Jansky was trying to find signals, like the noise, which disturb our cell phone signal, and then he observed a constant signal from our galaxy center. Then from there, then we have the radio astronomy. And in 1961, okay, for the photons, probably on the ground there's not enough. We go to the space, and the first gamma ray satellite Explorer 11 is launched. Then that's the starting point of gamma ray astronomy. And in 1962, the same time, okay, we have the ultra high energy cosmic rays and the X-rays. For X-rays, it's like we have an X-ray detector, and we got a robot. We send the X-ray detector go to the space and find signals from outer space X-ray signal. And then the same time, there are a few guys from MIT, they built a detector, and this figure shows the array configuration. So each dot is one cosmic ray detector, and they found, oh my God, there's a huge number, secondary particles. The energy, if you do the reconstruction, the energy of the primary cosmic rays can get up to 10 to the 20 eV. Wow, it's a huge energy for us. And then later we improved our method, we improved our technology, and in 1961 we have the first MEV, electron neutrino, by Davis, right? And he got the Nobel Prize quite a long time later. And it's the first time we get the neutrino from our sun. And starting from that time, we know, okay, we kind of have a multi-master astronomy because we have two masters, the photon and also the neutrinos. And later, I think everybody knows the supernova 1987. And we have the signals not only from our solar system, we also have some signals from outside of our solar system, right? So we got the neutrino signal, and then we got the light, we got other signals. So it's kind of like a starting of multi-master astronomy, even though people didn't mention that back to that time. And then, okay, we are going on to the ground-based instruments. Like in 1989, we have the first Cherenkov detector, like for catching the gamma rays with the energy something around TeV. So nowadays, the famous one is CTA, Cherenkov telescopic ray. But this is the prototype of the Cherenkov detector for the gamma rays. And then we move on. Surely before IceCube, there are some other attempts like Baikal, like Amanda. They are the precursor of the IceCube. But IceCube pronounced the first measurement of the TeV neutrinos in 2013. And they gave the name to the neutrinos, like Ernie. And then later, a few years later, it's not far, right? 2 years later, we got our first gravitational wave signal. But for the effort paid into this field, it has been a long time. I think from 1970s or 60s, people have already been working on gravitational wave, but it's really hard to measure. Even today, the gravitational wave is like, wow, it's a wimple, such tiny signal. You found that, and you do the reconstruction, you found the gravitational wave. So it's a basic picture of the multi-master astronomy from the beginning of the modern astronomy. And what we have today. So it's okay, if we want to talk about multi-master astronomy, we should start from the multi-wavelength astronomy. So we do multi-master astronomy study. What do we want to know? We want to know the properties or the mechanisms of those source or the source population. how they distribute, and how they behave, expanding with the universe and evolution going on. So here is a basic picture of cosmic photon background. We have a few bands. They have different names, as you can see here, like CRB, cosmic radio background, and CMB, most people know, cosmic microwave background, CIB, cosmic infrared background, and go on. So that's the whole picture. Where are they from? So that's why we do the population study, right? CRB. CRB. So basically, you know the mechanism. Who can emit the radio signal? And all of them form the background, living in our universe. The synchrotron radiation, right? Like our last lecture gave us a very, very nice presentation. So we have charged particle, and they move across our galaxy and the intergalaxy. With the magnetic field, they have their acceleration, and then they emit the radio signal. So those CRB is from the signals with those charged particle radiation. I mean, when they accelerated, they got the synchrotron radiation emitted. And the CMB, okay, that's from the Big Bang. After the Big Bang, when the temperature going down to 3,000 Kelvin, and then what happened? So the electrons and the protons, they will combine together and to form a neutral particle, right? During this process, there is no such photon scattering anymore, or there are quite less of them. And those photons are free. With the universe expansion, and now today we measure the CMB from that moment, and the temperature of CMB background is like 2.7 Kelvin because of the expansion of the universe. And then with a higher frequency, we get our CIB, infrared background. So those are from the stars through our universe or through our history. They emit those light. And most of them probably, if you have dust there, and you absorbed the light from the stars, and then they remit the infrared background. And the optical background is mostly from the stars, observable, I mean visible to us. And they are the second most important background if you compare the intensity. So here is the CMB. That's the most of them are CMB. And then later, the second intensity is the COB. Okay, with longer or with a shorter wavelengths and bigger frequency, we get our CUB, ultraviolet background. So those are from the light, hotter, right? The different wavelengths or different frequency means different temperatures. When your temperature is higher, you emit higher frequency, right? So you are going to the CUB, cosmic ultraviolet background. And then later the CXB, measured by Chandra and other X-ray experiments. How do they form? So it's like we have AGN, there is a accretion disk, it's super hot, and then they emit this kind of radiation from hot brimstone or other mechanisms. And then later we are going to cosmic gamma ray background. Those are from very energetic phenomena like AGN, blazar, right? Those emit those relativistic particles and emit with very high energy gamma ray in this range. And that's how we see our world. And those cosmic background are from the actual galaxy. So if you want to know our galaxy, or I have another question, for the higher energy, why there is no such band observed? In this range, why there is nothing? The more power you have, the more easy you will be absorbed. right? Or the more easy you will get interact. So if you want to have something with bigger energy, then you should wait for your chance. Okay, so that's the multi-wavelength observation. Let's go on with one of the example. I said we want to do multi-master astronomy for sure. We want to do the source population, but more practically, we want to know the source property. There is a very good example of Crab Nebula, and there are quite a lot of images of that. Like you have the observation from radio, infrared, optical, and ultraviolet, X-ray, and also gamma ray. What do they tell us? So from the image, and okay, this one doesn't show the coordinates of that. You have a guess. Which one has a bigger image? Radio? So from left to right, the energy of photons is going up. It's easier for high energy particles to move around, or not that easy? Not that right. So that's why if you compare them all in together, you'll know, okay, the radio has a big range, because it's easy for them to travel around for particles. I mean, the charged particles, electrons, protons, or whatever, right? So from here, okay, we kind of have a morphology study of those sources. And then what we have, so you can get the SED easily from this website. And those, okay, it will give you the SED, spectrum energy distribution. And there is one question. So this is already a challenge for us. If you observe this SED, which part is missing? Which ingredient is missing? MEV, right, super. So we don't have signals from Lisbon. I'll come back to that later, but you can think of that, why it's very hard to detect MEV photons. Okay, there is one hint. If you want to detect something, they should interact with your detector. Otherwise, they will go away. Right? Then why is so difficult for MEV gamma rays interact with your detector? Okay. And why is important for us? Okay. And from the morphology study, we can go into the spectral study. For example, here is the SED of the Crab Nebula with the energy extending to the PeV energy range. Like here you see it's 10 to the 15 eV. And the Crab is quite well studied. It's kind of new. It's like 1,000 years age. And it's very close to us. It's like a 2 kpc within our galaxy. It's already very, very, very close. And it's very bright. Especially if you see their spectrum, there are 2 humps. The 2 humps has already tell us a lot of things. Like if you can guess. So the first hump is from the synchrotron radiation. Why? Because we have particles which are accelerated by the magnetic field. Right? They will do the synchrotron radiation. And with this kind of radiation, you form the first hump. And the energies or the charged particles, they lots of energies, but there are still, some of them are still going on. And they will meet the photons they emitted from Lisbon, and they do the inverse Compton radiation, and then you get a second hump. From this hump, you can see, okay, we lost some energy for the synchrotron, and we lost some energy for the inverse Compton, and the ratio of them, you can know the ratio of magnetic density to the charged particle density. And then you can, from certain formula, to get the magnetic field of this source. And which we get is something around 115 microgauss. And with the B, right, and then you do the calculation, okay, for this kind of photon energy we detected on ground is 1.4 PeV. And then you estimate what kind of, or how high the energy of the electrons are, right? I can tell you a number, something around 2.8 PeV for this kind of electron neutrino. Okay, and if we see different energy band, the spectrum, okay, from the previous knowledge we know, okay, the radio is from the synchrotron radiation. What they tell us, the magnetic field strength, the charged particle distribution, and from the IR, which normally from the thermal distribution, right? We call optical normally from IR to UV. And those two are thermal radiation, and they tell us how the dust distributed, right? They emit or they absorb the starlight, and then they re-emit the IR radiation, and then how the composition is, how the hot gas distributed. And for the X-ray, as I said, okay, the hot or the thermal Bremsstrahlung radiation will emit this kind of radiation. They need very high energy or very high temperature. So normally they tell us the hot gas or the jet formation. And then for the gamma ray, you know they are from the inverse Compton. And okay, from this part we'll know what's the maximum energy of those relativistic electrons. And we can assume there is an electron distribution with a power law. So e to the minus alpha, and there is a cutoff for this part, and you do the fitting, you kind of know what happened for the Crab Nebula and how the morphology is. So that's usually what people do for the multi-master astronomy. But some people may ask, okay, here you are only doing the multi-wavelengths. So how the other particles or how the other messengers involved? Let's move on. And recent years, we have neutrinos and cosmic rays involved in this picture. So those are the neutrinos observed by the ice cube. And they tell us, okay, it's kind of like if you connect all this line back, all this line extrapolated. So it's quite consistent with gamma ray or with photons. And if you see the cosmic rays, why is a little bit higher than that? Because cosmic rays may come from our galaxy. And this is the overall cosmic ray observation. So there is a little gap, it's reasonable. And so here we can know, okay, cosmic rays, photons, neutrinos may from the same source. If they are from the same source, how could we solve this problem? Okay, then we perform our multi-master analysis. That's normally people do. Let's start from cosmic ray spectrum. People always say, if you write a proposal, you know, okay, we want to solve the origin of cosmic rays, then where they are from, then you should know what they are. Okay, those are the cosmic rays. They spend quite a lot of energy bands. So from 1 GeV to 10 to the 11 GeV. Then people may ask, okay, with lower energy, there is no cosmic rays? Certainly no. Just the spectrum is not that because our solar modulation. Our sun is quite close to us. When there are certain lower energy cosmic rays arriving, and they will banded or absorbed, interacted. And also in our Earth, we have the magnetic field around, then it's really hard to detect. That's why the spectrum is always starting from 1 GeV, and you can see, okay, we know the mass composition. Mass composition means what's the composition of your cosmic rays? You have proton for sure. You have carbon. You have oxygen. You have other ion, right? So okay, here. So it's kind of like our cosmic rays, and also you have the electron positron. So showing here. And with the energy spectrum, you can see, okay, with all the particles, if you add all of them together, you can see, okay, so the photon index here is, the slope is quite consistent. It's like 2.7. So that means probably they're from the same population, source population, right? So, okay, then we are okay with that, and we are fine with that. And then later, you see from here, something around 3 PeV, and to certain point here, you'll see, okay, the spectrum index looks going steeper, and from the photon index is from 2.7 to 3.3. Then what happened? Give a guess. Right. There might be related to the source, right? Because they are from somewhere. They are not just appear, right? So, okay, there might be something here. So there might be some other source population involved. And that's why we call this part is the knee. This one is the ankle. From knee to ankle region is kind of like a transition place from galactic cosmic ray to the actual galactic cosmic ray. And then later we are still seeing here, okay, the spectrum is going flatter again, right? So from here, going steeper, and then here flatter again. So that means the source population returns to some regular stuff, right? Okay, so this part is the transition part. This part, okay, we can say they are from the actual galactic. And then later there's another feature in this part. You can see there is a deep drop down or cutoff. That means if there are this kind of huge energy of cosmic rays, they will interact with our cosmic background, like I showed before, the CIB, COB, CUB, this kind of light. For them, it's really hard to get our Earth. So that's why there's a strong cutoff. We call it GZK, cosmic rays. And what else? Okay, if we agree, below the knee, those cosmic rays are from our galaxy. And from here to here, there is a transition. And after that, they are from actual galaxy. Then how should we perform the study of them? Okay, then let's do it one by one. It's not that difficult. For the galactic source, there are just a few options. Or from our understanding, there are only limited selections, right? Like supernova, remnant, star cluster wind, microquasars, and galactic center. Surely they emit a lot of radiation, a lot. And for the actual galactic source, also there are some quite well-known sources. AGN, GRB, starburst galaxy, and other pulsar, magnetar, this kind of very powerful phenomenology in our universe. Let's do it. Let's do it. If we want to perform the multi-master analysis, then we should know, okay, how we should do it. Then starting from the cosmic ray, how do they accelerate? There must be some mechanism for them to get energy, right? So this is a quite well-known mechanism for the cosmic ray acceleration. It's also called Fermi acceleration or shock acceleration. It's like in our galaxy, there is certain source, for example, supernova remnant or pulsar or whatever. And when they form a shock, they move together. And there is, on one hand, we call it downstream. And on the other hand, it's upstream. So on this side, the particles are not disturbed. And on this side, because shock is moving this side, they are kind of like compressed with a lower speed. And here, if you have a particle, for example, here, they move around here because the magnetic turbulence, like the magnetic field is quite irregular. If they pass from the shock, here is a shock from here to here, it's like from higher speed to lower speed. So they don't lose or don't gain any energy. But the magnetic field confines them around the shock. There is a chance they will come back. When they come back, So the speed of the particle here is higher. And then when they cross, they will gain the energy. So if they cross a lot, like over and back, the energy then is gained by them. It's quite reasonable, actually. If you study it in details, you know the spectral index of this kind of accelerated particle is just follow the power law. Okay, and it has been studied by some authors here. If you are interested, you can look into the detail and think of how make the model and anything else. Okay, if in our galaxy, the particles are accelerated in this way, can they explain the cosmic rays we observe? Let's do a very simple calculation. For example, in our Milky Way, one time supernova explosion will inject, they will put a lot of energy outside. It's like 10 to the 51 Earths. And for the supernova rate in our galaxy, it's like we have 1 century, there are kind of 2 or 3 supernova explosion. And you think of that, if the cosmic rays is emitted from the supernova remnant or from the supernova explosion, is there a chance they will leave our galaxy? There might be, right? And then we'll kind of study, okay, how long will they take to escape our galaxy? Don't make it too complicated. Just, okay, in our galaxy we have the gas, right? We have the dust, and we have all these kind of magnetic field. And then you do the calculation. For example, for the supernova explosion, the energy of cosmic rays can get up to 10 to the 15, let's say PeV energy. And for one particle, you take all these kind of process into account, you will know, okay, they probably will take 15 million years to get away of our galaxy. And within those 15 million years, how many supernova will happen? That's a lot, right? So 100 years, we have 2 or 3. Each of them will emit 10 to the 51 Earths. And then you kind of do the rough estimation, and then you will know, okay, it probably is okay. All the supernova may contribute to all the cosmic rays. And then that can solve our problem of our galactic cosmic ray. Then the problem solved. Then that's why, okay, that year, so 1934, people think, okay, the supernova explosion, so we'll solve the cosmic ray mystery. And from observation, okay, it's quite the case, no problem. And people happy with that. That's why you always heard of, okay, in our galaxy, the supernova remnant emit the cosmic rays, and they have those kind of cosmic rays in our disk plane, and have our other observations. Okay, let's go on. And here is okay, let's do it one by one, no rush. Here is the X-ray cosmic ray observation. Let's see it. For example, we can relatively easy to identify proton or helium. And here is the observation for the proton, here is the helium, and here is the electron and the positron. People may ask why you don't show the carbon and the iron here. Because for them it's a little bit hard to identify. You know, there are a lot of charge and rigidity, then it's not that clear as proton and the helium. And that's what we see. Okay, if you see there's a gap between the blue and the yellow, that's because for different experiments like Cascade and Ice Top, they use different models, ironic models. So when they do the analysis, they found a gap between them, but sorry, the discrepancy is not that big. So we have the cosmic ray injection from, okay, we assume it's from the supernova explosion. And what we do. So for example, So here is quite a clear picture, or yeah, it's a brief picture. There is a supernova remnant. They emit a lot of particles. And for example, so like those proton, helium, CNO, carbon, oxygen, and those particles also include electron and positron. They will leave the source. They will enter our galactic interstellar medium, and for surely they will enter the magnetic field. They will have some energy loss process like the diffusion, reacceleration, convection, production of secondaries, blah blah, and also within the magnetic field or interstellar radiant field, gas. They will have the synchrotron radiation, inverse Compton, Bremsson, or they may interact with those gas or dust and produce those pions. Pion will have my favorite neutrinos, right? Those neutrinos with higher energy and also gamma rays. And those signals will be detected when they arrive at our Earth. So we have all kind of equipment, Pamela, ACE, like a HAS, Chandra for me, and on the ground we have Ice Cube. So, okay. So if we do the calculation, we kind of know what happened. And we can perform a simulation. And before we do the simulation, let's make a model, geology model. For example, our galaxy, the size of our galaxy. So you know most of the sources are located in the galactic plane, right? So the galactic plane, we have like a 2h. The height of that is 2h. It's something like a few kiloparsec, like 1 to 3 kiloparsec. It depends on your model, but that's fine. There's no big difference. And the radiance of our galaxy is the RD. Okay, we assume our RD is 20 kiloparsec. It's reasonable, right? That's from our understanding today. And when there is a supernova explosion, they emit the cosmic rays. All the particles or charged particles will confine in the disk. They will have all this kind of process, right? Like what I showed you before, fragmentation, decay, interaction, and synchrotron radiation, all this kind of process. And there is also a chance for them if they move with the magnetic field and then they leave our galaxy. So, okay. Most of the magnetic field is concentrated in our galactic plane. For this part, there is quite a weaker magnetic field, so we don't take that into account. And that's our model for the galaxy. Then we perform the simulation. There are a few equations maybe some people would like to see. So here is our, I may take that out. Here is the propagation equation. On the left side is the cosmic ray density, changing with time. And on the right side, you all know, okay, there might be source, and there may be other way to loss. And we take everything to the right-hand side. So Q is the injection function. As I told you, we assume there is only supernova explosion can emit the cosmic rays. And we have the supernova remnant distribution. The distribution, here the function is the spatial distribution, changing with the height z and the radiance r. And the r star here is the distance from our Earth to, or our sun to the galaxy center. And here r is the distance of the supernova remnant to the galaxy center. And then the injection function, let's say for one supernova remnant, how much energy they emitted. We assume it's Qj. And these two combined together give us the QRP, right? The injection function for different source at a specific location. That's our injection part. And there are some other parts like, okay, they will undergo the diffusion. The diffusion parameter, also there are two parts. One is a spatial distribution. If we assume our galactic plane is uniformly distributed, then there's one way. If you assume close to the galactic center is more condensed and far away is more less dense, then you make your model. And beta is the, beta v over c, the velocity of the cosmic ray over the speed of light. And the D0 is a normalization factor or the coefficient factor. R is the rigidity. Delta is from the secondary ratio. So if somebody doing research in this field, you all know, okay, if you have a carbon, they will interact to produce boron. And the boron to carbon ratio can tell you the evolution of the cosmic ray, right? It's a how to say? It's a plot, or it's something like you have the ratio on your y-axis. On the axis is the energy, and you all know it's quite a stable slope function. And you all know, okay, how the secondary to the progenitor particle give us the evolution of cosmic rays. Then that slope give you the delta here, changing with the rigidity. Okay. Oh. Okay. That's the diffusion part. So here V is the convection velocity. So there are some waves and other wind give us the V here. And also there is a chance they do the acceleration for the cosmic ray particle. There might be some turbulence and the magnetic reconnection. And there is also some other way to lose energy, like the synchrotron radiation, Ewers-Compton, Bremsellon. And then the particles may undergo the fragmentation and decay. Here the tau is the fragmentation or lifetime of the particle, and here is the decay of the lifetime of the particle. And we have everything here, and we know the cosmic ray density, right? You have already observed. And you put everything into the Gauss probe, they will do the simulation, and then you compare with the observation. So here is the galactic plane observation, right? So this one is quite popular from the 2023. And the ice cube tell us they confirm the galactic contribution of neutrino, right, with 4.6 sigma confidence level. And so those other sources, those other images are from optical, gamma ray, and here is analysis, right? And they look quite consistent. And if we compare our calculation with their image observed, what we'll do? So here is the kind of figure they have. And this one is the ice cube total neutrino, means the all sky neutrino observed, right? Not only galactic neutrino, also included the actual galactic neutrino. So if we don't see any other model, we compare these two shaded region, we can know, okay, our galactic distribution might only contribute like 10% to the whole sky. So most of the neutrinos are from actual galaxy. So our galaxy is only a tiny contribution to the neutrino flux. And okay, from our model, right, we will learn everything. And we will have a model. So here is our model. DR means diffusion plus reacceleration, which are the two most favorable process for the cosmic ray. We give a name called DR. And with that model, you found, okay, with our everything included in the last page. And here is our calculation. It's probably not enough. We cannot match the total nu here. There might be something missing, okay? Then how we solve the problem? Okay, maybe some people will say, okay, for ice cube, there are three models. They have pi0 model, they have KRA model, right? KRA model and the pi0 model means the different spatial distribution. For pi0 model, they assume in our galaxy all the diffusion is quite uniform. But for the KRA, they assume different model. And if somebody is familiar with this field, you already know, okay, these three has quite a big discrepancy. They don't agree with each other that well. Then how we say that? Then that's another thing. Or the challenge is appearing here, right? What we want to do? If they observe something but give us quite three different results, then what we should do?
Get the average of them.
Which model fits something?
Fits what? Energy spectrum.
Looks like there's still discrimination.
You choose your favorite.
If you can actually measure the energy very well, looks like they're not super. You can differentiate them, right?
Right.
All
Right.
the way to it.
Right.
It's like if you have a shape, you could differentiate.
But we have to very confident about our model or simulation. Then.
I thought you want to differentiate the model.
Uh-huh.
Then you base on the data, look at the shape.
Look at this shape.
Yeah.
Okay.
No. That's the only handle. It's diffusive. There's nothing else you can do.
Well, at least for me, there is one thing we can do. We can wait for more statistics.
Sure.
So I think it's too early to say, okay, which one is the best. But we do need more statistics to solve this problem. And the first challenge is right here. So how we get more statistics? So you need a bigger detector within shorter year, right? Okay.
So is the fact that only 10% of the diffusive flux come from the galactic plane, that's the expected fact? Is that expected? Because you said that it's dense. In principle, you have a lot of scatter there.
Right.
Somehow you're seeing a more diffusive. Presumably, those guys are coming from X.
Well, before the real observation, there could be some theoretical study about that.
Yeah.
Something around that.
So 10% is expected.
Yeah. Well, the range is quite big. It's from 5% until 20. So 10 is reasonable number. Okay. So that's the galactic plane observation of from ice cube. Then if we want to have more solid or robust observation, then you need more data to solve this problem. Or in our study, we say there might be different source contribution. The one with actual 1 with a lower cutoff, and the actual 2 is another model with a higher cutoff energy. These two source population might be solve this problem. Okay. So yeah, more statistics is needed to give a model independent of neutrino distribution. Okay, and that's for the source population study. If we want to have a source, okay, what should we do? There are a few input. Actually, it's not that difficult to do. So when you have the observation, normally it's SED, energy over fluxes, and you want to fit that. What you do? So you have a model. You build a model. So a few factors you have to take into account. And the first one is the cosmic content, like how much particles you have, like how do they distribute it, with a power law or power law cutoff, exponential cutoff, something like that. And what do they have, like electron, positron, proton ions, and what are their luminosity? So the energy budget of that, right, or per second, how many of particles they have. And that's the first one. And then you should consider the environment. Like if you want to have the particle interaction, for example, PP or P gamma interaction, you should know how many cold particles there are in the environment, right? In this case, they can interact. Otherwise, it's super hard. And also, what's the magnetic field involved, right? Magnetic field decide your synchrotron radiation. So how will they lose their energy? And if you have a jet, they will have a Lorentz factor, like the Baikal-Lorentz factor, they move together, right? So then that's a few factors you have to take into account. And the source geometry is quite flexible factors, like what's the size of the jet, are they symmetry or not, maybe only one-sided, and the injection zone is close to the black hole, or there's a distance from the black hole, where do they get accelerated, get maximum energy, how the magnetic field distributed. And also there are a few other angles, like a pitch angle, viewing angle, and that decide how, how your flux is and how the particles are accelerated. And the other one is the time evolution. If they transient or steady source, it's quite different mechanisms. So, okay, if you have these 4 factors and then with relevant processes, then you'll get your output, your observation, let's say, or multi-master observation. Okay. So usually you'll see a paper. They give some parameters in this table. So those parameters are for these few factors, these 4 factors, and they will introduce how the processes are, blah, blah, blah. And if you are interested, you can take any paper and read how they do the model. So for example, Data is a Doppler factor, R is a radiance, magnetic field. So this part is the electron or proton distribution, energy distribution. And here is the luminosity, magnetic field. And here are the expected neutrino events. Okay. So before we are moving to real access, let's review some process. Elena has already introduced synchrotron radiation. So let me show this picture. Normally we say leptonic model means the radiated or the moving particle are leptons. So it's like electron, positron, and what they will undergo. So when, surely there is a magnetic field, they will undergo synchrotron radiation, and also they will undergo the inverse Compton, and also Bremsstrahlung, right? When it's super hot, all the particles are in plasma state. So there might be strong electromagnetic field, right? When an electron comes in, there might be a Bremsstrahlung. Bremsstrahlung is like an electron stopped, right? They will emit the radiation. And also the electron-positron pair will annihilation to produce photons. Those are the 4 major processes for the leptonic model. Now let's first take a look at the synchronous radiation. So Elena has do a very good introduction. Let's maybe briefly introduce here. For one single particle, for example, we have an electron. The synchrotron radiation spectrum is something like that. It's proportional to the magnetic field, and also proportional to the sin alpha. The alpha is the angle between the electron projection and the magnetic field. And here, x is like a factor in this formula. And fx is from Baikal integration. It's kind of like if you do the simplification, you get 1.8 times blah blah this. And then you get your formula here with the shape like that. And you can see on the lower energy or lower frequency, the spectrum is proportional to the frequency 1/3. Okay. And with certain critical frequency at this point, nu-c, the critical frequency, you get the maximum, right? Below and after. After is proportional to the exponential minus x. And when x get to 0.3, you get a maximum. It's around 0.9. Okay, that's for one electron. If you have a lot of electrons doing the synchrotron radiation, right? Then you combine them all together, right? If the electrons have power law distribution, then for one, you have this single single spectrum, and then you add all of them together. So here is a power law of the electron distribution. You should get the synchrotron radiation, something like that. And then later you will see, okay, it's not what we observe. Oops. Okay. Okay, so you have already, yeah. So for the shape, why there is a turnover here? Because the absorption, which is called synchrotron self-absorption. So during when the energy is low or the frequency is low, the photon is more easily to be absorbed. Then in this part, the synchrotron radiation is proportional to the frequency to the 5/2. Okay. In this part, when the optically thin, and the photons can easily get more free, and the spectrum is proportional to the 1 minus 2 over 2, 1 minus k over 2. Okay, so that's the case. Let's continue going on. Then why there is a cutoff, something like that? It's constrained by the size. So the electrons cannot get, let's say, PeV or even higher 100 eV, right? Because they have gyro radiance. When your gyro radiance is bigger than the size of the source, they will escape. They cannot get maximum energy like forever. There is no limitation, surely not. Then there is a cutoff, something like that. That's what we observe for the synchrotron radiation. But wait, there is not the case. Sometimes you will see your synchrotron radiation is something like that, because when the electrons have more energy, they will lose their energy easier, right? So that depends on the age of your electrons and the energy of the electrons. And for different age of the electrons, probably for the higher energy, they will have the cutoff even shift to the left. So that's why when you do the observation, especially for the radio, if you observe different part of the sky, you get different synchrotron radiation because the age of the electrons are different. So, okay, the one closer to the core or further from the core have a higher age. Then you can expect your synchrotron radiation, how does it look like? Right? That's a question for you guys. That's one of the synchrotron radiation. And then we move on to Bremsstrahlung. For the Bremsstrahlung, it's like, okay, I told you it's from a very hot plasma. And for different temperatures, they will give you the different shape or the spectrum. For example, from here is lower to higher, 10 to the 5 to the 10 to the 7 Kelvin. And here is, I'll take it out. Here is the formula for Bremsstrahlung. Okay. What do they tell us? So for the Bremsstrahlung, this part is for single particle, single electron emit energy. So it's proportional to the T to the minus 1/2. When you have higher energy, higher temperature, your J is lower, right? Then that's why it's a bit lower. And why this part is proportional to the nu square, also because of the self-absorption for this part. And then this point can be calculated. It's, so alpha nu is the Einstein absorption coefficient. R is the radiance of the jet or whatever. And when it's equal to 1, you find your nu in this point. And everything, if you see for the higher temperature, for surely this this integration should be higher or should be bigger than the lower temperature one, right? They emit more energy in this sense. Okay, that's Bremsstrahlung. Let's go on with the inverse Compton, right? We have leptonic model. So for the inverse Compton, we know, okay, there are a few models like a one-zone model or two-zone models, right? So yeah, maybe you guys know about that. For one-zone model, is normally it's self-synchrotron, self-Compton. So within the jet, the same population of electrons emit synchrotron radiation, and then later they will hit the photon they emitted to get them boosted to higher energy, and then you get your Compton, inverse Compton radiation, like the gamma rays, right? Which is called SSC. But sometimes if SSC cannot solve your problem, you get a higher gamma ray flux, what you would do? You build a model with more parameters involved. It's like we do the external inverse Compton. For example, if you have a jet, also some along the, so here is a black hole, you have accretion disk, you have a broad line region, and here is a torus, they would contribute some radiation, right? At least they have black body radiation. Those are your target photons, and your electrons will interact with them via inverse Compton process and emit the higher energy gamma rays. So those are the inverse Compton. And you will see your inverse Compton, the shape of your inverse Compton preserves the spectral index of the Thomson regime. It's like they follow the shape of your electron, right? They will have the same shape. So here is the inverse Compton. Let's go with the hadronic model. Hadronic model means you have more material like a proton and other ions involved. And there are a few main processes like proton synchronization. Surely, any charged particle moving in the magnetic field, they will emit the synchrotron radiation. But you can see here, it's proportional to the mass over one over mass. So you can see, so which one emit more synchrotron radiation, electron or proton? Electron, right? They have less mass. So normally why we will say, okay, even if we have some protons in the jet, they have smaller contribution because their mass is too big. Okay, that's the proton synchronization. And Bader-Hettler pair production is like you have a proton will interact with a lower energy photon. And it's like you give some energy to the photon. The photon will interact with other photon to produce the electron and the positron pair. Or you will have some, you will interact or you will meet other nuclei and produce the electron and the positron pair. Bader-Hettler pair production, sometimes it's not that dominant, but sometimes, especially if you learn about the study of NGC 1068, it will decide the maximum energy of your proton. We'll come back to that later. Okay, and what else we have? The photon pion neutrino or the high energy pion production. It's quite well known, okay? So we have the PP and the P gamma interaction. So everybody familiar with that? We have the delta resonance and produce pi 0, pi plus, pi minus. They have the ratio of 1 to 1 to 1. And then those pions will decay to the gamma and the neutrinos. And then at the production site, we know, okay, we have 2 muon neutrino and 1 electron neutrino. After the oscillation at Earth, we have the ratio of different flavors is 1 to 1 to 1. And the gamma takes 10% of proton energy, and the neutrino takes 5% of the primary proton energy. And there is a thing, if you build your astrophysical model, it's like where does the gamma or the P from? Right? You should have something. So, okay, PP or P gamma interaction, surely you should find your target. If there is no target, then what to do? Right? That's another thing you should think about. When you do the PP or P gamma interaction to produce neutrino, surely neutrino is good, but how do we get that? If the density of proton, target proton or target photon is too low, there's no, probably there is no big chance to have your neutrinos, right? Then for protons, PP, this proton is from the cold particle, which moving in the jet, we call it cold particle, right? There are a certain energy distributed to them, and there is a number density of those protons. And sometimes, okay, for the synchrotron radiation, Ewers-Compton synchronization, you already have your target photons. Those can produce those PP and P gamma interaction. And some people would say, okay, PP and P gamma interaction have different cross sections, but why? Which one is dominant? Okay, it depends on the density of your target particles. Okay. And then we want, okay, we have no, okay, our galaxy have a certain cosmic ray distribution, and we know, okay, supernova remnant is a good candidate. Now we really seriously to see our map, and we want to find one, and we want to solve the mystery of cosmic ray origin, right? And then we look at the map. At least you should look at the gamma ray map, right? Okay, from last slide, okay, PP and the P gamma interaction will produce gamma rays and neutrinos at the same time. How about we have an easier way? Okay, let's look at the gamma rays. If there is a chance neutrino would be opponent with the gamma rays, then that's easier, right? So, okay, here is the LASSO catalog map. They found 90 sources and with very high energy gamma ray emission. Among them, 32 are new discoveries. And we found, okay, we just do some cross-check, and we found there is a source, one LASSO J 1929, 1846, which has, by chance, has one neutrino, has an event associated with that. And okay, let's do our model, right? 4 factors: cosmic ray content, environment, and how the geometry, and then later what's the force? Transient or steady, right? So that's 4 factors. Let's do the study. We assume if this one is indeed a neutrino source, and what we should do. First, we search for the archive data, and from that region, what we can see. There is a radio observation, and okay, this one is a supernova remnant. In the center, there's a pulsar, and they blow out the wind, the pulsar wind nebula, and also you can see there is something like a ring here. Okay, that's the radio data. And then we observe our X-ray data. Okay, it has a smaller region in this part. And if you do see the IR, infrared observation, okay, I already told you the infrared observation, where they're from, right? From the dust, blah, blah. And it's a combination figure. So in the center here, the blue region is for the X-ray, and the radio is the reddish region. And we can see, okay, it's quite good. The pulsar wind nebula can be distinguished from the supernova remnant. Supernova remnant is like after the supernova explosion, they emit all the material outside, right? So the material, like all the particles, matters, they will go away. And there is a pulsar inside. They will rotate and blow out the electron or charged particle jet, right? So this one is quite like a jet. And then let's do the work. Let's construct the source geometry. And here we combine with the lasso observation, and what do we find? So here is the molecular cloud, and here is the source for the lasso region, and here is the Pauser. Sorry, the figure is too small. Here, the inner core or inner circle is for the Pauser Ring Nebula, and these purple lines for the supernova remnant. And we find the cloud here. That's our target proton, right? As I told you, if the neutrino is indeed from this kind of source, there should be cold particle, or at least you have target photon, right? Otherwise, there is no chance to produce neutrino. And in our model, we said, okay, if radio and the X-ray can observe or can distinguish from the Pauser Ring Nebula and the supernova remnant, let's do the work. We found the cloud, which serve as the cold particle, and we do the integration from the observation, and we know, okay, for the western cloud, here is a west cloud, so here, they have a mass of 10 to the 4 solar masses, and for the corn cloud, this part, which is overlap with the Pauser Ring Nebula, they have the mass of 10 to the 3 solar masses, because they have a smaller region and the cold particle is not that much. And let's do the calculation, okay? If you only fit with the Pauser Ring Nebula for the radio and the X-ray, because they have the observation from that, the only synchrotron radiation can solve the problem without any problem. You just have to assume electron distribution, right? It's a power law. And we fit this part and find our alpha 1 and alpha 2, which is 1.7 and 2.7. And we integral get the total energy of those charged particles and do the fitting, find the magnetic field of this Pauser Ring Nebula is 100 microgauss. And then later, for the supernova remnant shell part, is outside part, there is only X-ray observation and IR observation. IR is from the dust, and which set as upper limit for our case. And we do the fit as well. Okay, there is electron model, leptonic model, and we fit our data. And also for this higher energy part, they are from Fermi and the Veritas. They can fit quite okay, but we cannot fit, or we cannot agree with the lasso data. Then there is something missing, right? We should consider the contribution from the cloud. And then for the contribution from the cloud, then the hadronic model is assumed. We assume the proton follows the power law and solve the equation, partial equation, and find the energy of the proton, the fitting parameters like here, the A and the B. Okay. And then later we calculate the neutrino, we calculate the gamma ray flux from our cloud model and find that they are quite okay. Even though in this part is from the WCDA, they don't agree with each other well, because WCDA have a have a bigger uncertainty. If we have the uncertainty included, that could be matched well. And if we contain the ice cube observation here, it's quite okay. And if we want to solve this kind of problem to find the origin of galactic cosmic rays, the challenge is also here. You need a bigger telescope, right, to have more sensitivity, find this problem, and solve the origin cosmic ray problem. Okay. Yeah. So I will stop here. So next time I will talk about the other cases for other multi-master study. Any questions? Thanks a lot.
Thank you very much for the lecture. Questions?
Yeah, thank you for your lecture. So I have two not really big questions. So can you spread data if you need to explore the particular object, but recently supernova explosions? Can you spread the data of supernova object you need to explore. If you need some objects
Yes.
and supernova, if explosion, you will detect its data too. Can you separate the data of the object, like any galaxy or something, from supernova data?
You mean for photons or?
Maybe.
It means, I think, that when there are two objects simultaneously happen, supernova explosions and some other objects of study, can you disentangle between them?
They are from same direction?
Maybe close.
Wow, we are so lucky. They are the same type of sources or two different type of sources? Well, okay, if they are the same type of source, let's say there are two supernova explosions at the same time at the same direction. Is that?
Yeah.
Okay. Well, if they are the same time, for example, they have the same progenitor mass, and they have different distance, right? And then we can identify the flux, right? So the flux is luminosity over 4 pi d squared, with a further distance, and then your flux is lower, right?
All right, and the second question, you told that no more than about 10% of the diffuse flux is from galactic plane. Where is other flux come from? Like natural radiation and something?
You mean where the other 90%?
Yeah.
Okay. So, okay, I'll talk about that tomorrow. So we have a lot of sources in our actual galaxy, like gamma ray burst, AGN, right? They are superpower. And there are also one part of our cosmic ray spectrum, right? So after Ni, we have the ANCO and GZK. So those would contribute to the neutrino as well. Like for the chemistry net, recently observed the 100 PeV neutrino, right? They definitely from the actual galaxy. Or might be a chance from our galaxy, but with lower probability, right? Yeah.
Yeah,
Thank you. More questions?
Okay, thank you for your presentation. Maybe I have a small problem for detecting the neutrino sources, like by the multi-messengers. If there are like two different neutrino sources in the same direction, based on like Earth, how can we distinguish these neutrinos from the near neutrino source or the far neutrino source?
It's a good question. So we only have, okay. I have to say we are super lucky. And first we have to, there is no chance they are from the atmospheric background, right? And also the second is we have to assume they are from two different sources at the same time.
How can we distinguish this neutrino from the near source or the far source with the same direction?
That's probably super hard. That's why we cannot use neutrino to get the redshift or the distance of the source, right?
Yes, so maybe we can use like the gamma ray to distinguish these two sources.
Normally we use optical.
Okay.
Mm.
Thank you.
More questions?
May I ask two questions? First is how wide range how looks in the sky? How wide in stereo rating, angle?
How wide?
Yes, it's. I don't think it's look for the whole sky. I think it's looked on some region. Yes.
Mm-hmm.
And the wide the size of this region? So it scans the sky, or just looking in one point in the sky in some angle?
For
I think he's asking for the field of view of lasso.
oh, field of view of
Yeah.
okay. Field of view. I think it's you mean zenith angle. Zenith angle is probably for the region knows more 45.
Nearly the whole sky.
Yeah. Right.
Monitor the sky. The monitor the whole sky at the same time. And in normal data analysis, we choose the zenith angle smaller than 55 degrees. So it's more than closed area.
And next question, maybe you know how long it looks, if there is a region then it stops for technical reason or for maintenance, or in working 20 hours, 7 days and 200 a whole year. How long it's in continuous work?
For lasso?
Yes, gathering data.
Oh, for lasso is 90% or even higher, 94 or 95% of duty cycle. You mean that?
So the next question is interesting for me. So you have collecting data about some region of the sky, and you may, from some collected statistics, say what is the random average luminosity of some region. On this, using this data, you could understand which maybe some new source is found, because you see this was nothing there, and next time you see some signal. It's maybe in some smells question this our participant asks how to distinguish these two signals. If you have background information, average on the sky, you could always see that something new, something new coming.
Yes, right. Yeah, it's a very good question. So for ground-based telescopes, normally we claim a source or identification with 5 sigma. Yeah, so which can overcome the background. The background is super high, so when you have a 5 sigma, you can say, okay, that's definitely a source, right?
Any more questions? We have time for a couple more.
Thank you. I have a question. Maybe you're going to review this next lecture, but anyway, assuming that some neutrinos of alpha energy comes really from the galaxy, and also we have Baikal GVD, which enhances this statement. So what could be the source there?
What could be the source? So the well-known source is a supernova remnant, and nowadays people think microquasar, the binary system, can be the potential sources. I think if you have enough powerful jet, and then there might be enough cold particle, and then you can generate those neutrinos. Some work while it's still going on, right? So, yeah. I think probably our sensitivity is just on the edge, a bit lower, a bit.
So thanks for this talk. I have a very naive question. You mentioned the Zwick's postulation that supernova explosion, if you count the number, count the energy, and they make 100% this PeV energy photons. What happened afterwards? What this picture has been updated. The question is, what's wrong with this picture? And my follow-up question is that normally we talk about supernova explosion, we're talking about 20 to 50 MeV neutrinos, so on and so forth. So is it still true that the cold-collapsing supernova can produce higher energetic neutrinos?
Surely. They are in different phases. Like you have, for example.
So what's wrong with Zwick's picture now? I mean, now people's understanding apparently updated from his original story, that there's so many possible sources of PeV and higher protons, right? Cosmic ray is the problem. Right? There's no cosmic ray problem. We don't have to solve all the mysteries. The problem is cosmic ray. So what's wrong with this picture?
Nowadays, it's still reasonable.
It's still reasonable.
Yes. Yeah, it's not that far away from our observation, so it's no big fault for that.
So assuming that then we just wait to see if when the next neutrino, the low energy neutrino sees the supernova neutrino, whether there's high energy neutrino, telescope can see a PeV neutrino, that could solve the problem?
Probably we need more evidence. You know, after 1987, you know, people are still working on that.
Assuming at that time
Right.
there's also a high energy neutrino telescope that's working.
Mm.
In principle, you should see the coincidence if this model is correct.
Should be, if there is a core collapse and then first MEV neutrino will emitted, and of course with gravitational wave, and then later they eject material, those material will form shocks.
How far away these two events should be?
How far away? You mean distance or the time?
Time.
Time, a few seconds.
Wow.
Mm.
Okay.
Yeah, depends on the mass.
Yeah.
Mm.
Interesting.
Mm.
Okay.
So that's why people think, okay, multi-master
Yeah,
gravitational.
certainly. So different wavelengths of neutrino is very important, right?
Sure.
You use the Juno type of detector to detect the thermal component.
Mm-hmm. Because for example, for the kilonova, right?
Yeah.
2 seconds later, 2 seconds after gravitational wave, you have the gamma ray. I guess gamma ray should be together with the neutrino. There's no big problem. Mm.
Thanks. Very interesting.
Okay, let's thank the lecturer once again.